Good evening, sir.
Today we will discuss on determinant rank.
Sir, some noise is coming.
Okay. Let's see. Is it okay now?
No, there is some white noise, like white noise kind of thing is coming.
Now, is it okay? Sure.
It's not gone. Is it a fan or something? I don't know. Like,
Okay, okay. Okay. Now I think it is clear. Let us start. What is determinant?
sir, can I ask you a question? Last week assignment में
Yes, yes.
That row space rank is equal to column space rank. Can you please help to understand?
Okay. Yes, it is true that you can define rank in many different ways. One of the measure rank is same as rank of row space, and this is actually same as rank of column space. And there is another rank which is called rank obtained from determinant, or you can say it is matrix rank. It is also same. So why row rank and column rank is same? It is your question. So it
Yeah.
is same because when you are doing row operation, for example, take any matrix. I can give the idea. So take any matrix 1, 2, 3, 4, 5, 6, 1, 1, 2. Suppose this is a matrix. When you are doing some row operation, then you can see that number of non-zero rows in row echelon form and number of column in which pivot element are. Suppose I don't know what will be row echelon form for this matrix. Suppose there is some matrix and you are doing some row operation, and after that you will get a row echelon form in which first row and second row is non-zero and other rows are zero. Then from here you can see that first and second column or first and another column will contain non-zero pivot. So
Yeah.
from this you can say that non-zero, that is when you are doing row operation or column operation, you'll get same non-zero rows or same number of columns in which pivot there exists non-zero pivot. If you use this fact, I think it will be. You can use this fact to prove row rank and column rank are same. This is the idea. I have not given the whole proof, but the idea is that you
Sorry,
Yes.
actually, in the question number 5, if you see,
Question number 5. What
yeah,
was that question?
it is saying A is a real square matrix with full rank.
Yes.
So, like if we go on reducing it to reduced row echelon form, it will have non-zero rows. It will have one and it will lead to identity matrix, right?
Yes.
So then number of you're saying that rank of row space is
Yes.
equal to rank of column space if it
Yes.
is full rank.
Yes. Yes. If it is full rank, then rank of row space is same as rank of columns.
But is it true for always? Like,
It is. It is always true. For
okay, okay.
example, yes. Because
No special condition where
that
they are
is.
not.
I am not saying that number of non-zero columns. I am saying that number of columns in which pivots there are non-zero pivots. For example, suppose after some reduction A, after few reduction, it gets we are getting this matrix 1 2 1 1. There is 1, there is 0 1, and there is 0. So after reduction, suppose you are getting this matrix.
Hmm.
Okay, and this will be 3 4 0 0, and everything except those are zeros. Then from here you can see that number of non-zero rows in this matrix after when we are reducing, after reduction we are getting number of non-zero rows, it is same as 3, and also number of columns which contains the non-zero pivot, that is
Hmm.
this column and this column,
Hmm.
this is also 3. Okay.
So, is it always true? Like, no matter what kind of matrix it is?
Yes, it is always true, because now if you do row reduction also, then you will get only those rows will be independent. Okay.
Okay, okay.
Only
And one of my
those will,
other question was not correct. In question number 3, if you can see on your screen, because it has multiple choice. So, if you can open that question number 3, then we can see because it has multiple choice answers. Many answers are there.
question number 3. Okay. Assignment 4, no?
No, last quiz, which quiz number 3, assignment 3.
Which question?
Question number 3.
Question number 3. So,
Can you share your screen so that we can see the
okay.
options?
A and B are M cross N matrices. This is the question. Sorry. A, B are M cross N matrices. Now, A, B have the same row space. Then they have the same row reduced REF. It is true. So, A, B have same row space. this will automatically imply they will have same row echelon form. It is true. Then now next question is AB have the same reduced REF, then they have the same row space. B B is also true because same row space, sorry, same row echelon form. Then row space is linear combination of those rows. Therefore, they will have same row space. It is also true. If we have the same row space, then they have same row echelon form. REF. Okay, there are two uh, different notion. One is reduced row echelon form, and another is REF, which is row echelon form. So I think here row echelon form REF refers that only reduced. That is
So, sir, like if A and B are two matrices,
yes,
they can have the, I was thinking like reduced row echelon form can
yes,
be identity matrix for both of them, right? Like once we go to full rank row reduced echelon form, RREF,
yes,
then it becomes identity matrix, correct?
yes. It is
So
true.
in that case, RREF can be same.
Yes, RREF always be same.
Can be same. So first is correct only.
Yes,
But second one, I was thinking that if RR, so the second one says A and B have the same RREF, then they have the same row space. This may not be true because uh,
okay,
identity,
okay. Yes,
right?
what you are saying, the thing is that row space means not those rows. That is not first row, second row, and third row. Row space means that linear combination of those rows.
Acha. But that may also not be necessarily same, right? Because identity matrix can come anyway, right? In RREF.
Yes.
So we don't know what kind of linear combinations are available in A and B. So how can we contend that they have the same row space? Can we confirm
Okay.
that? Can,
Okay. This is true. That the thing is, if
you
you
got
use
my
those,
question? You got my question, right?
yes, if
Okay.
you use those elementary steps,
Yeah.
elementary reductions, then the row space. So if you are using row operation, then row space of A is same as row space of the row echelon form. Suppose R, and those will be same. Why? Because when you add, suppose you are, what are the row reduction procedure?
Yeah, that I understand because they are just like
Yes, linear combination of another
yes,
thing. Yes, this
correct.
is true. So what is your, now? What is your problem then?
Sir, just give me 1 minute. 1 minute.
Yes. So you are saying A, B both leads to I after reduction.
No, sir.
Then
Sir, I'm saying that the second option B is
yes,
not talking about REF. It is talking about RREF, right? So
yes,
since they are saying कि A and B have the same RREF,
yes.
that doesn't mean that the same elementary operations were performed on both, which will lead to the same row space,
No,
right?
it is not saying that. It is saying that they have the same. So suppose B and A both leads to identity after row reduction.
Correct, correct. Yeah,
Then
that's my.
they are saying that
Hmm.
row space of B is same as row space of A.
Is that guaranteed? I mean, I
Yes,
okay.
it is guaranteed because uh, what you can do, you can see that after reduction, the row space of this A and row space of the reduction is same. And
But
again,
this
for
is
the first one is also same.
sir, this is reduced row in option B, they are not talking about REF, they are talking about RREF.
Yes, whatever you use, that is RREF or REF. Okay.
But given I, can we really distinguish between A and B because end result is same, but how it began we cannot tell, right?
For example, let us consider an example.
Okay.
Suppose is 1 1 0 1, and another matrix is 2 1 0 1. If you reduce it, then this will give the identity matrix, and this will also give the identity matrix. Now, this will imply row space of this matrix is same as row space of identity matrix. Similarly, row space of this matrix is same as row space of the identity matrix. Therefore, those are same. Therefore, it will be again same. No?
Hmm.
Any elementary, if you perform any elementary reduction, it will give the same row space. Row space is not changing. That is why Ax equal
Sir,
to B.
my question is like any matrix which is going to full rank
Yes.
row reduction,
Yes.
uh, reduced row elementary form, it will become a identity matrix.
If it is full rank matrix,
Yeah.
it
So
will become identity matrix after reduction. It is true.
yeah. So then we say that all those matrices are all same, like
They
their
are
linear.
not same, but if you consider linear equation, suppose Ax equal to 0 and another matrix which is same as identity A2 or A dash x is 0, these two equation will give the same solution. This is the meaning of equivalence. Yes. Those are row equivalent, means these two equation will give the same solutions,
Hmm.
but they may not be same. For example, if you see that if you if you if you
Yeah,
consider,
I got what you're saying. Like linear combinations will produce like,
yes,
so does that mean we can say a linear combination of A will give a linear combination of B also?
yes, that is what it says. Yes, you are right.
Oh,
Linear combination of A and B are same. Okay, let
okay.
us.
So, sir, why have they excluded, like included D also? D is there. Okay, D is fine. But C, option C.
Option C, if A and B have the same row space, then they have this same row echelon form. Option C, it may not be true because reduced row echelon form, it is different from only row echelon form. When I am saying REF,
Ah,
there is two notion REF and RREF.
correct. So you are saying REF may not be same.
Yes, REF may not be unique. There are different row echelon form, but if reduced row echelon form is unique. Okay.
Yes.
For example, this I think this will be a REF, and this is also a REF,
Yeah.
but this is only RREF, but this is not a RREF.
Okay. So only my confusion was with option B, but looks like if RREF is same, then even A and B are have the same row space.
Hmm. Yes.
Okay.
It is.
Thank you.
Okay. Welcome. So determinant of a matrix. Consider a smallest example will be consider a 2 by 2 matrix, a 1 1, a 1 2, a 2 1, and a 2 2. Then determinant of A is same as a 1 1 times a 2 2 minus a 1 2 times a 2 1. That is, you are doing multiply those two things. then subtract this. Okay, this is determinant. So what does this represent? Suppose consider this R2 plane and there are two vectors. One vector is given by a11, a21. It is coordinate of this vector. That is, this point is a11. This point actually a11, comma a21. And similarly, there is another vector, and coordinate of this vector is given by the second column a12, a2. Then the parallelogram formed by these two vectors, the area of this parallelogram is represented by this determinant. And similarly, you can consider a 3 by 3 matrix also. A11, A12, A13, and similarly A31, 32, 33. Okay, then it will give the volume of this three-dimensional object. It is difficult to draw this. Determinant of A will represent the volume of this three-dimensional thing. Okay, and you can notice that if you change the first and second row exchange, then determinant after exchanging, it will be negative of the determinant of matrix A. Okay, why? Actually, this determinant, this does not only represent area, it represents the orientation of two vectors. That is, the second vector, it is left side of the first vector. This represents that information also. That's why if you exchange those first and second row, the sign will be negative. Let us check this. So suppose A dash, consider A dash. It is A21, A22, A11, A12. Then you can see that determinant of A dash, it is same as A21, A22 minus A12, A21, A12 minus A22, A11, which is same as minus of determinant A. And this is true for any n by n matrix. So if you change any two row, exchange any two row, then sign determinant will be same, magnitude is same, but the sign is different. Okay, A change to B, then determinant of B is same as minus delta. And there is another property which says determinants of A plus C times some row. Suppose Ri denotes a row of this determinant. Okay, Ri or Rj. Then this remains same. This will be same as determinant of A. How can you see? So suppose you are adding this is the parallelogram. Now you are adding some multiple of this second line. Suppose we are adding this. Then the new parallelogram is now this. This will be the new parallelogram. And you know the fact the area of this parallelogram is same as area of the new parallelogram. This is clear from the geometry. So we can say this. Determinant of A plus C times some row is same as determinant of A. And there is another property which will be important. Determinant of C times A. Sorry. Suppose A is given by those rows R1, R2 up to Rn. There are n rows. Then if you multiply one row by C times R1, and all are same, then determinant of this matrix, this new matrix, is same as C times determinant of A. This is also clear from the geometry, because if you stretch one side by, suppose C is the stretching factor, or if you stretch it two times, then area will be twice, because this area, the older area, is half of the new area. That is what it says. So you can see now, if you use row operations, that is row exchange, then determinant will be negative. And if you add some multiple of a row with some rows, then determinant will be same. And if you multiple a constant with some row, then determinant will be C times that determinant. Those are some properties. Using these properties, you can say determinant of a matrix. Suppose there is a matrix which contains zeros in a row, and other things we don't care what are other things, then determinant of this matrix is same as 0. Why this is true? This is true by this fact, because you can pull C outside, and C is now 0 in this case, because the second row is 0 times everything. So you can pull out 0 here, so this will give 0. And another thing you can say, suppose two rows are same, suppose Ri and Rj are same, and other thing we don't know what are the other rows, then determinant will be same. If two rows are same, Rj is same as Ri. Why is it true? Because determinant of this matrix Ri Rj is same as determinant of, if you exchange those two rows Rj Ri, then it will be same except a negative sign. But it is given that Ri is same as Rj. So we are getting something is same as negative of that thing. It is only possible when this thing is 0. Something cannot be negative of that thing. It is not possible except it is 0. So those are the important properties of determinant. And explicitly you can write, there is a formula, nice formula. Suppose A is given by aij's. Aij's are the entries and ij varies from 1 to n. Then determinant of A, you can write it by this formula, minus 1 to the power, it is sine of the sigma, and there will be a1 sigma 1 up to an sigma n, where sigma is permutation. Okay, sigma belongs to permutation of n letters. This is the definition of determinant.
So, can you please help understand this definition a little bit with example?
So consider this matrix A11, A12, A13. That is the previous matrix. If you consider this matrix, then determinant of this matrix is same as, it says choose. So suppose you are taking those three things, A1, A2, A3. Now you can map 1 to 3 to 1 to 3 by 6 ways. That is, there are only 6 ways for bijection. One way is send 1 to 1, 2 to 2, 3 to 3. Then it will be 1 to 1, 2 to 2, and 3 to 3. And there are other possibilities also. For example, send 1 to 1 to 3. So there are 6 ways. So another way will be send 1 to 2, 2 to 3, and 3 to 1. So 2, 3, and 3 goes to 1. And another possibility will be like this: 1 goes to 1, and exchange only those two things. 2, 1 is 1 goes to 1, 2 goes to 3, and 3 goes to 2. So there are 6 possibilities. That is 3 factorial ways for this permutation. And you need to take sum of all those permutations, and you need to consider the sign also. Sign of the permutation. So sign of the identity permutation is plus 1. So it will be plus 1. And here 1 goes to 2, 2 goes to 3, 3 goes to 1. This permutation can be written as, if you use the sign for this permutation, it is same as 1 3 into 1 2. There are even numbers of transposition. We call it transposition. So sign of this permutation is also positive. But here there is only single exchange. You can consider it as a row exchange. That is, only 2 rows are exchanging. So there will be a negative sign for determinant. That's why it will be negative. Similarly, if you consider another example, in this example also you can see that there is 2 exchanging. That is, 1 goes to 2, but 2 is also goes to 3. Okay, so there will be 2 row exchange. You can thought it as this. So that's why sign is same as positive. And similarly, suppose you consider this also, 1 2 3, 1 goes to 2, and 2 goes to 1, 3 goes to 3. Then also 1 goes to 2, 2 goes to 1, and 3 remains same. Then also there is only single, so first 2 rows are exchanging in this case. That is why sign will be negative. Is it clear? So there will be 6 those types of entries corresponding to the bijections.
Okay, but in the blue color, that formula,
Yes.
how we read that formula? Like what is
Okay.
S
So
sigma?
you are taking all those A1 up to N, and where those 1, 2, 3 goes. That is, if you consider 1 goes to 1, 2 goes to 2, 3 goes to 3, you will write this thing. And you need to consider for all such permutations. That is why I am writing all such things, and this formula writes those things together.
Okay.
Okay. Sigma
Yeah.
denotes those functions actually. Sigma
Okay.
denotes those functions, and sign of the sigma is given by how much change, how how much row exchange or how much change is needed. If there is even number of changes, then it will be plus, and if it is odd number of changes, then it will be negative.
Okay. Yeah.
So if you use this definition, you can prove many different things. There are different properties. Determinant of a plus b is same as determinant of a plus determinant of b. So another property is determinants of a times b. This is same as determinant of a times determinant of b. So those are the properties, field properties you can prove using this formula. Determinant is again distributive. What does this mean? Determinant of a times b plus c. This is same as, okay. This is clear from the distributive property of matrix. This is not a new thing. So those are the properties of determinants. And now let us consider some examples. For example, question: what will be the determinant of question number 1, skew symmetric matrix? So you can let us make it a MCQ type question. Choose the matrices for which determinant is 0. Always yes. Another thing is symmetric matrix, nilpotent matrix, and there are two different classes. For example, unitary matrix and another thing is so orthogonal. Which of the following have determinant 1, determinant 0? So what will be the answer? You can see that skew symmetric matrix may not have determinant 0. Why? For example, consider this matrix. This is a skew symmetric matrix. Determinant of this matrix, what will be determinant of A? This is same as 1 times minus 1 and negative. So this is same as 1. So skew symmetric matrix may not have determinant 0. So it is wrong. And what What about symmetric matrix? This is also wrong because consider identity. Determinant of identity matrix is same as 1. So this is also wrong. Now what about determinant of a nilpotent matrix? Nilpotent matrices are such matrices for which a to the power n is 0 or a to the power some k. A to the power k is 0 for some k. Now, if you apply determinant on both sides, then determinant of a to the power k is same as determinant of 0, but 0 has determinant 0. That means now you can use the product rules. Determinant of product is same as determinant of the individual things. It is same as det a to the power k. Something to the power k is 0. This always means that thing is 0. Therefore, nilpotent matrix, it is true. For nilpotent matrix, determinant always be 0. And for unitary matrix, what will be determinant for unitary matrix? So consider what is unitary matrix. Unitary matrix are those matrices for which A and A star, A into A star is same as identity. Now, if you apply determinant, then you will get determinant of A times determinant of A star is same as determinant of I, which is 1. But this is same as determinant of mod A. Determinant of A, mod of determinant of A square is same as 1. This actually means determinant of A has modulus 1. That is, this is also a wrong answer. This will be, it will be false. And another thing, what about orthogonal matrix? So orthogonal matrices are those matrices for which A transpose is identity. And if you apply determinant, then determinant of A times determinant of A transpose is 1. But what does this means? Determinant of A transpose is same as determinant of A. Therefore, determinant of A square is same as 1, which means determinant of A will be either plus 1 or minus 1. Then this is also a false answer. So only 3 is correct answer. But if a skew symmetric matrix is n by n matrix and n is odd, then what will be determinant of that matrix? So question is determinant of A when A is skew symmetric and this n equal to odd. Then what can you say? So we are familiar with the property determinant of A transpose is same as determinant of A. But note that A is skew symmetric. So A transpose is same as minus A. So determinant of minus A is same as determinant of A. Now minus A means all n columns are negative of the previous. So if you pull this negative, then it will be minus of determinant of the previous thing. So it will be plus and those will be negative. And again, if you take the second negative, then it will be minus 1 square, determinant of plus plus, and the third negative. And now take another negative sign, then it will be determinant of everything plus now. So in general, for n by n matrix and when n is odd, it is n by n matrix, then it is same as the left hand side determinant of minus A is same as minus 1 to the power n determinant of A. It is same as det A. But given that n is odd, therefore minus minus 1 to the power n is same as minus 1, and minus 1 times data is same as data. Hence, this will imply 2 times data is 0, therefore data is 0. Okay. So this will imply n by n skew symmetric Okay. Now consider another question. Those are few classes of matrix for which we know what will be the determinant. Okay. So another question is, suppose A is an upper triangular matrix. What does this means? Below the diagonal everything is 0. Okay, and there is something below the diagonal everything is 0, and we can denote it by Aij is 0 when I is greater than j. So for example 2 1 and 3 this is 0, 3 1 and 3 this is 0. So when I is greater than j this is 0. Now the question is, what will be determinant of this matrix? So given A is Aij, Ij varies from 1 to n, it is n by n matrix, then what will be determinant of this matrix? So let us try to see. A11, A12, A13, A22, A23. Let us consider only 3 by 3 case. General case can be easily seen from this case. So this can be written as A11 if we are expanding the determinant with respect to this first row, first column. Then it will be A11 times the determinant of this, then 0 times determinant of the rest of the things. So it is same as A11 times A12, sorry, A22, A23, 0, A33, and everything except these are 0 because we are expanding with respect to first column. Similarly, again if we expand with respect to the first column, we'll get A11 times A22 into A33. And in general, for n by n matrix, this will continue up to n. Therefore, determinant of A, it will be A11, A22 up to AN. Okay. So determinant of upper triangular matrix is product of the diagonal entries. Determinant of upper triangular matrix it is same as product of diagonal entries. Now, what about lower triangular matrix? Determinant of a lower triangular. We can now use the fact determinant of A is same as determinant of A transpose. So if you take transpose of lower triangular matrix, it will become upper triangular matrix. And you know that when you are applying transpose, the diagonal entry remains same. Therefore, determinant of lower triangular matrix is also same as product of diagonal entries. So those three things are same. Now let us solve an example. Given this matrix, A is 1, 1, 1, A square, B square, C square. Find the determinant of A. What will be the determinant? Det A is same as 1, 1, 1, A, B, C, A square, B square, C square. Now we can perform the elementary operations. That is, elementary operation means you can add one row with another row, multiple with another row, and another thing, you can exchange two rows, but exchanging will give a negative sign. You need to remember that this fact. So 1a square, if you perform r2 minus r1, then determinant will be same as the previous, and if you perform r3 minus r1, then also determinant will be the same as previous. So now this will become 0, b minus a, b square minus a square, and this is 0, c minus a, c square minus a square. And again, if you now you can take b minus a and c minus a, you can pull it outside, and it will become 1a square. Now the second row, because the second row is multiple of b minus a, so we can take it out, take b minus a out. So it will be 0, 1 b plus a, and similarly 0, 1 c plus a. Now this is now easy, because if you expand this determinant with respect to the first column, it will be just 1 b plus a and 1 c plus a. But this is same as c plus a minus b plus a. That is c minus b. Okay. Those types of matrices are called Vandermonde matrix. Vandermonde. Those can be obtained from a polynomial. So for Vandermonde matrices, there is a general formula. 1, 1 up to 1, and this is same as x0 square up to x0 to the power n, then x1 square up to x1 to the power n, and it will continue up to n step, xn square up to xn to the power n. So determinant of these types of matrices is same as product of xj minus xi, where j is strictly greater than I. Okay. An easier way to see this is if you put x0 in the place of x1, then these two rows will be same. Therefore, there will be a factor x1 minus x0 by the same reason. the factor b minus a, this occur because if you subtract second first row from the second, then you can take b minus a outside, and similarly c minus a, and here this will continue. So you can take x1 minus x0, you can take x1 minus x0. Similarly, if you subtract from the second row, you can take x2 minus x0, and it will continue up to xn minus x0. Similarly, instead of x0, if you subtract the third row minus second row, and then you can take x3 minus x1, x4 minus x1, and up to this end step, you can take all those difference xj minus xi, where j is strictly greater than I. And you can now compare the diagonal entry, because determinant will have a diagonal entry which is same as 1 x1 up to xn to the power n. And here you can check what will be the coefficient of that entry. If those are matches, then this is the formula. If those are not matching, then you need to stretch this factor. That is, you need to multiple something such that determinant matches. Okay, this is how we can show this. Or there is another way to prove this by induction. Using induction, you can assume up to n minus 1 step, and then you can conclude about nth step. You can try this problem also. Let us try another problem. So given, instead of general matrix, let us give this matrix. Given 0 0 a0 minus 1 0 a1 minus 1 0 minus 1 a2. The question is to find determinant of a plus c, a plus ti. What will be determinant of a plus ti? Let us check. So what is a plus ti? It is same as diagonal entry will be t. Okay, so t will be added with the previous. So it is t plus a2 and 0 a0 a1 minus 1 0 minus 1. Now what you can do, you can perform the operations, row operations, such that determinant remains same. For example, uh, let us remove this minus 1. Okay, so for this, what you can do, you can just multiply t0 a0. You can just multiply t with the second row, then it will be minus t minus minus t square a1 t. But if you multiply second row with t, determinant will be t times the previous. That's why we need to divide it by t. Okay, though this is not allowed because we don't know if t is 0 or non-zero, but we can do this because you can just multiply t here, and you can say t times this is same as this. So let us consider t is non-zero, and we can take t outside. And similarly, if you multiply t square with the third column, then it will become 0 minus t square, and this is t cube plus a2 t square. So we have multiplied t square with the third column. So determinant is now t square times from the previous. That is why we need to divide it by t square. So 1 by t square. That is 1 by t cube times this is same as, now we can use the row operation, that is r2 minus r1. So r2 plus r1. If we do this, then it will become t0 a0.
Sir, the A33 element
Yes.
that you have multiplied by t square. Okay, fine. Yeah, no problem. Thank you.
Okay. So now this is 0 0, and this is a0 plus a1t. We are adding r2 plus r1. We are doing this operation. So this operation will not uh, change anything for this determinant. So it will be same as a0 plus a1t. Similarly, r3 plus r1. If we do this operation, we'll get 0 r3 plus new r2, that is this new row. Okay, we are considering this new row, not the previous r2. Instead of doing in another step, we are doing together. Okay, then this will give 0 0, and sorry, there is a t square here. So 0 0, and this is same as t cube plus a2t square, and there is another a1t. Now you can see that this is, if you expand determinant with respect to the last column, last row, then this is same as 1 by t cube times the last thing, t cube plus a2t square plus a1t with this thing. Okay, so determinant of this thing is t cube. So we are getting the determinant of a plus ti is same as t cube cancel out. So this is same as t cube plus a2t square plus a1t. Okay, this will be the answer. I have done something wrong here. Oh, there will be a0 because there is a0 plus a1t. So there is another a0. Okay. In general, you can prove using the same step. You can show that determinant of this kind of matrices. So if you consider solve this problem, 0 minus 1 0 and everything is 0, then 0 0 minus 1 and everything is 0, and it will continue up to 0 0 0 minus 1. Now here is a0 a1 a2 up to an. If you consider this matrix, then determinant of this matrix a plus ti, it is same as a0 plus a1t plus a2t square, and it will continue up to t to the power n. Okay, you can check this. The same idea will work. Okay, there is a question which say what will be, you know, adjoint, right? Adjoint of a matrix, adjoint of A. Consider this matrix A, which is same as Aij. Explicitly, let us try 3 by 3 matrix A11, A12, A13, A22, A23, Then you can take cofactor of any entry. So let us construct a new matrix C such that you can denote Cij, the entries will be same as, you just delete those row and column. For example, C11, consider C11, it is same as deleting first row and first column, that is A22, A23, determinant of this. Similarly, C12, you just delete first row and second column. Then we are getting A21, A23, A21, A23, A31, A32, A33, sorry. And you can do for every entries, and you can form a new matrix C. C, those C11, C12, those are called minors. And if you also take the sign of this minor, for example, minus 1 to the power 1 plus 1 C11, minus 1 to the power 1 plus 2 C12, and it will continue minus 1 to the power I plus j Cij, it will continue. Those entries are called cofactors, and transpose of this matrix is called adjoint matrix. This C is called adjoint matrix. Okay, so let us compute an adjoint matrix. Consider this matrix. Let A is same as 1, 2, 3, 4, 5, 6, 1, 1, 2. Then what will be adjoint of A? So it is same as minus 1 to the power 1 plus 1 into everything except first row and first column. So it is 5, 6, 1, 2. And similarly, minus 1 to the power first plus 2, 1 plus 2, and everything except first row and second column. So 4, 6, 1, 2. Similarly, minus 1 to the power 1 plus 3 times 4, 5, 1, 1. Determinant of this. And if you continue in this way and take transpose of this, okay. So the this entry, what will be this entry? This entry will be 2 times 2, 4 minus 3. So it is 1. Next entry will be 1 times 2, 2 minus 3. 2 minus 3 means minus 1. And this corresponding to this entry will get 1 minus 2. That is minus 1. But we also need to take the sign. That is why here the sign was plus, minus, plus. Now the sign will be minus, plus, minus. Okay. So here there will be a minus. It is plus time minus 1. It is minus 1. There is another minus. So it will become plus 1. Similarly, if you consider this thing, then it will be 2 times 6, 12 minus 15. So minus 3. Corresponding to this, we are getting 6 minus 12. That is minus 6. And corresponding to 2, we are getting 5 minus 8, minus 3. But there again we need to consider sign, plus, minus, plus. Because minus 1 to the power, this is same as minus 1 to the power 3 plus 1, which is plus. That is same as plus minus plus. So second entry, there will be a sign change. it will be plus 6. Adjoint A will be transpose of those things. Now if we do 10 minus 6, it is same as 4, and 8 minus 6, it is 2, and 4 minus 5, it is minus 1. And again there will be sign change, here it will be negative, and minus 1 to the power 2, it is same as plus. So this is the adjoint. Therefore adjoint is same as 4 minus 1 minus 3 minus 2 minus 1 plus 6 minus 1 plus 1 minus 3. Okay. And there is a nice property of determinant which says A times adjoint of that matrix is same as determinant of A times identity. That is, if you multiply A with this adjoint matrix, you will get identity matrix with some multiple of this. The multiple is given by determinant. So let us consider an example. So let us see through an example. A equal to 1, 2, 3, 4. Then what will be A adjoint of A? So adjoint of A, it is same as this cofactor of this entries. So it will be 4, then 3. If you consider 3, it will be 2. If you consider 4, it will be 1. Transpose of this, but we need to consider also sign. So plus minus plus plus minus, then minus plus. Because here minus 1 to the power 1 plus 1, it is plus. Minus 1 to the power, then minus 1 to the power 1 plus 2, which is minus, and this will continue here also. So adjoint can be written as 4 minus 2 minus 3 and plus 1. Therefore A times adjoint A, let us check what is A times adjoint A. It is same as 1, 2, 3, 4 times 4 minus 2 minus 3, 1. And this is same as 1, 2 times 4 minus 3. What is this? This is same as 4 minus 6 minus 2. Similarly, 1, 2 times minus 2, 1. 0. Then again 0. 3 into minus 2 minus 6 plus 4 minus 2. So this is same as minus 2 times identity matrix, because if you take 2 out, minus 2 out, then it is same as identity matrix. And let us check what is determinant of this matrix. You can see determinant of A is also 1 times 4 minus 2 times 3, that is minus 2. Therefore this theorem is holding for this case, and this will be true for any matrices. You can prove this theorem considering the arbitrary that general formula. Now if you use this formula, then the question is what will be the inverse of a matrix given A. Then question is what will be inverse of A. Can we write inverse of A in terms of A? The answer is yes. There is one way to write this. We know A times adjoint of A is same as determinant of A times I. Now if determinant of A non-zero, then we can multiply 1 by det A both sides. This will give A times adjoint A by det A is I. Now again multiply A inverse both sides. Then this will give adjoint of A by determinant of A is same as A inverse. So this is how we can find A inverse. Instead of row reduction, we can use this formula also. Okay. So now you can see that whenever determinant of A is non-zero, that is when A is non-zero, A is non-singular, that is determinant of A, whenever determinant of A is non-zero, then A is invertible. And the inverse is given by this formula. Adjoint A divided by determinant of A. Okay. Let us find inverse. So if you consider this example A, what will be inverse of A? Using this formula, we can say that A inverse is same as adjoint of A by det A. Now adjoint of A is given by this, determinant is minus 2. So this is same as 1 by minus 2 times the adjoint, 4 minus 2 minus 3, 1. So A inverse is same as 2 minus 1 minus 3 by 2 and half. This is A inverse. So instead of doing row operations, we can use this formula also for finding inverse. Let us consider this question. What will be the determinant of adjoint A? What will be the determinant of adjoint of a matrix, given matrix? So you can use this formula because we know adjoint of A times A, this is same as det A times identity. Now apply determinant with apply determinant. This will give determinant of A times adjoint. This is same as determinant of, so instead of determinant A, just write C. Okay, where C equal to determinant of A. So this is determinant of C times A. Now what will be determinants of C times A? I. This scalar matrix. C times I, you can see that C times I is same as CC in the diagonal. And everything except this is 0. So clearly determinant of C times I, this is same as C to the power n, because you can you just, as we know that the upper triangular matrix, determinant of an upper triangular matrix is same as product of the diagonal element. So diagonal element are C, C everywhere. That is why determinant of Ci is C to the power n. Okay. So this is C to the power n. And the left hand side, now we can use the property determinant of product is same as determinant of the individual. Now if determinant is non-zero, if we consider this, suppose C is non-zero, given determinant A is non-zero, this is also given. Okay, then this is same as determinant of adjoint A. You can now divide. This is same as C to the power n by det A. But what is C? C is actually det A. So this is det A to the power n by det A. So this is det A to the power n minus 1. Another question is, what will be determinant of A inverse? Again, you can use the fact A times A inverse is identity. Now apply determinant on the both sides. It will give determinant of A times determinant of A inverse is same as determinant of I. What is determinant of identity? It is 1. Hence, determinant of A inverse is 1 by det A. Okay. As A is invertible, 1 by det A exists because det A is non-zero. Those are the nice formulas. There is an important concept, rank of a matrix. So suppose A is a matrix Aij, n by n matrix. Now rank of A, it is largest n by n, largest R by R submatrix which is non-singular. Okay, this is a definition of a rank. Definition of rank of a matrix. And the interesting thing is that this rank is same as row rank. Okay, row rank. Okay, there is a, so let us compute rank of matrix using determinant. Okay, given a matrix 7 1 4 6 minus 3 0 minus 3 5 minus 2, given this matrix. Now what will be determinant of this matrix? This is same as determinant of this matrix is same as 7 times 6 minus 1 times we are expanding with respect to the first row, minus 1 times minus 12 and plus 4 times 30. This is same as 42 plus 12 plus 120. clearly this is non-zero. Hence, rank of A is 3. Because now the largest R by R submatrix for which determinant is non-zero is actually this 3 by 3 matrix itself. Therefore, the rank of the matrix A is 3. Consider another example. 1 1 2 1 1 3 4 5 2 2 4. Now you can see that the third row, it is 2 times of first row. Therefore, determinant A is 0. Hence, rank cannot be 3 because the largest R by R submatrix for which determinant is 0 is not actually 3 by 3 matrix itself. So now we can take the smaller blocks, okay, smaller submatrices. So we can try this submatrix. If we take this submatrix, then we can see 1 1 2 2. This is actually 0. But if we take this submatrix, then 1 2 4 5, determinant of this thing is actually 5 minus 8, which is minus 3, non-zero. Hence, the largest submatrix for which determinant is non-zero is actually 2. Largest R, okay? Largest R by R matrix for which this R by R submatrix is non-singular. For this case, actually R is 2. Hence, rank of A is same as 2. Okay. So those are the nice things. Instead of performing row operation, you can just check determinant wise. That is, determinant of, first we need to take determinant of the whole thing. If it is non-zero, then rank will be 3. Now if it is 0, we will take the submatrices. We will try to find a smaller submatrices, 2 by 2 matrices for which determinant is non-zero. Then rank will be 2. If even it fails, then rank will be smaller thing. So rank will be automatically 1 because there exists a non-zero entry. Okay. For this case, we are able to find a 2 by 2 matrices for which for which determinant is non-zero. Okay. That is why rank is 2. Another thing we can do is solving an equation. So suppose A is n by n matrix and the given equation is Ax equal to B. So when does this equation has a solution? When does this equation has a solution? So the solution will exist if and only if A is non-singular. That is, A has full rank. Okay. Because the fact is, if A has smaller rank, suppose A has rank n minus 1, then clearly, though A has rank n minus 1, but A, B, when B is non-zero, let us consider B is non-zero, then A, B, this has rank n. Therefore, clearly, this system has no solution because augmented matrix and the matrix has different, those matrices have different rank, okay, when B is non-zero. So when B is non-zero, this system is solvable if and only if A has rank n. And from the definition, this is same as saying determinant of A is non-zero. That is, A is non-singular. Okay. Let us try to find a solution. There is a rule which is called Cramer's rule. We can use this rule to solve any n by n system. Suppose consider this system x plus y plus z is 11, 2x minus 6y plus minus z, this is 0, 3x plus 4y plus 2z is 0. Now solve this system. Okay. Answer. So this system can be written as 1, 1, 1, 2 minus 6 minus 1, 3, 4, 2 times xyz is same as 11, 0, 0. This is A, this is x, and this is B. Okay, this is A times x equal to B. Now, what is the determinant? Determinant is 1, 1, 1, 2 minus 6 minus 1, 3, 4, 2. And this is same as 1 times minus 1 times minus 12 plus 4 minus 1 times 4 plus 3 plus 1 times 8 plus 18, which is same as minus 8 minus 7 plus 26. Okay, so determinant is non-zero. Therefore, this system, this star, therefore star has an unique solution, as the result is written here. So the system has unique solution if and only if determinant is non-zero, determinant of this A. Now the Cramer's rule says to solve this system, we just do those types of things. So the solution is given by, so replace the first row here, replace this row, x is same as, replace the first row 1, 2, 3 by this 11, 0, 0. Replace the first row with b, small b. So it is 11, 0, 0, and except the first row, everything is same. 1 minus 6, 4, 1 minus 1, 2, and divide it by the determinant. So determinant is 11 by date. Okay. Sorry, determinant of this thing also. This is actually determinant. Now, if you compute, this is actually same as 11 times minus 6 minus 2. 11 times minus 6 into 2 minus 12 plus 4. By determinant of A is 11, so it is same as minus 8. Similarly, Y will be same as, replace the second column. Second column was 1 minus 6, 4. replace it by 1100. And except this, everything will be the same, 1, 2, 3. And the third column is 1, minus 1, 2. And divide it by determinant. Now this is, if we expand with respect to the second column, this will be same as minus 11 times 2 times 2, 4, plus 3. So this is same as minus 7. Similarly, Z, what will be the Z? Z is same as 1100 and 1, 2, 3, 1, minus 6, 4. It is same as 11 times 8 plus 18. It is 26. Therefore, the solution is x equal to minus 8, y is minus 7, z is 26. If you put those things here, those equation will be satisfied. Okay. So this is the new thing. Okay. So those are all the things about determinant. Now let me say about linear transformation. Actually, determinant will be used in linear transformations. That is the reason we have done determinant first instead of doing linear transformation. So what is linear transformation? Consider two vector space V and W be two vector spaces over the same field F. Then consider a map T which maps from V to W. Consider this map. And this map satisfies the property, that is, if you add first and apply T, then this is same as apply T first and then add for all V comma W from the vector space V. And if it satisfies another property, multiple any vector with C and then apply T is same as first apply T and then multiply with C. If those properties are satisfies, then T is said to be a linear transformation. So linear transformation means it is not only map from a vector space to another vector space, but it needs to satisfy some structure. That is addition. It satisfies the addition property and scalar multiplication property. That is, it is commute with addition and scalar multiplication. This is the definition of linear transformation. So the natural question is, why 0 will goes under the linear transformation? So let us see. So T of 0 plus 0, this is same as T of 0 plus T of 0 by this property. Now T of 0 plus 0, 0 plus 0 is same as 0. So T of 0 is same as T of 0 plus T of 0. Now we can cancel one of the T0. This will give 0 equal to 3, 0. This will imply under linear transformation, 0 remain fixed. So what are the examples of linear transformations? Consider the stretching, that is, suppose R to R, consider this map, T maps R to R, such that T of x is suppose 4 times x. Then this is actually linear, this is a linear transformation. Why? So let us check those property T of x plus y. Suppose x plus x comma y belongs to R. Then this is same as 4 times, by definition this is 4 times x plus y. And by distributive property it is 4x plus 4y. Now what is 4x? 4x is actually t of x by definition, and this is t of y. So first property is satisfied. Okay. Now we need to check the second property, that is scalar. It respects scalar multiplications or not. So t times some constant x. C belongs to the field f. F is here real number. This is actually 4 times cx by definition. But this is same as c times 4x. And this is same as c times tx. Okay. Hence, we can say t is a linear transformation. Now, consider this operation. So, T maps R to R. Instead of stretching, let us shift. So, define T of x is x plus 4. That is shifted by 4. Then, is it a linear transformation? You can see that T of 0 is same as 0 plus 4, which is not 0. Hence, we know that under a linear transformation, 0 remain fixed, or 0 is invariant under linear transformation. Therefore, T is not a linear transformation. Consider another type of things. For example, consider this transformation. T map R2 to R2 by rotation. So what is the rotation by theta? It is rotation by theta. It is actually given by txy is same as x cos theta plus y sin theta, comma minus x sin theta plus y cos theta. Okay. Then question is T a linear transformation? So let us check. Again, we'll do those things. Instead of doing those two things in different ways, we can put it. This is actually equivalent to T of Cx plus y. That is, linear combination is same as C times Tx plus y. We can put those two different relation in a single relation. Okay. We need to check this single relation. T of Cx plus y, T of some linear combination will be same as linear combination after applying T. So let us check this. Prove T of, consider those two different vector x1 y1 and x2 y2 from the real number R2 and C from the field R. Then what is TCx plus y? This is V1, this is V2. Then TC V1 plus V2, this is same as C times x1 y1, this is Cx1 Cy1 plus V2. V2 means x2 comma y2. Now if we apply the transformation by this star, we'll get first one times cos theta, that is Cx1 plus x2 cos theta. The second one times sin theta, Cy1 plus y2 sin theta minus of the first one, Cx1 plus x2 sin theta plus the second into cos theta. This is a tuple. So now if you distribute, this will be nothing but C times x1 cos theta comma y1 sin theta. Sorry. C times x1 cos theta plus y1 sin theta comma minus x1 sin theta plus y1 cos theta plus x2 cos theta plus y2 sin theta minus x2 sin theta plus y2 cos theta. Hence, we can say that rotation is a linear transformation. Rotation of a plane, it is actually a linear transformation. Instead of just rotation, you can see this is actually, you can write it explicitly as a times xy. Okay, where actually you can write the same x comma y. This actually goes to a times xy, where a is same as cos theta. T is the T maps from R2 to R2. Here the column entries we are taking as a column entries, and T maps x comma y to a times this, and here a is cos theta minus sin theta cos theta. Sorry, cos theta plus sin theta. Yeah. So clearly, this T actually T of xy, it is same as multiplication by this matrix A into xy. Now using this definition, using this structure, it will be useful to check this. That is, it is now easier to check those properties. That is, take x1 y1 and x2 y2 from R2 and C from R. Now what will be T of this? T of, that is, this is P1, this is P2. Now what is T of CP1 plus P2? This is actually matrix multiplication with A. That is A times CB1 plus B2. Now we know matrix multiplication is distributive. So this is same as C times AB1 plus AB2. And what is AB1? It is actually C times AB1 by definition. It is actually T times B is A times B. TV is the same as A times B. Therefore, it is TV1 plus TV2. Hence, any matrix multiplication is a linear transformation. Any matrix multiplication is a linear transformation. Okay. So let us consider some example which will be non-linear. So suppose, listen, are those linear transformation or not? Example 1. It says t x1 x2. So we are considering R2 to R2. T maps R2 to R2. T x1 x2 is given by reflection. That is x1 goes to x2, x2 goes to x1. Is it linear transformation or not? What will be the answer? Another thing is given by projection. x1 comma x2. This actually goes to x1 comma 0. That is first one is reflection along this line. Okay, it is reflection. That is x comma y. This goes to y comma x. And the second one is projection. It is project everything onto x-axis. This goes to x comma 0, x comma y. This actually goes to x comma 0. Projection. Are those two operations linear transformation or not? What will be the answer? So as you can see that this thing actually can be written as if you write in column form, then x1 comma x2, this is t of this is same as we are denoting the coordinate by x1 x2 this column. This is same as x2 comma x1, and x2 comma x1 this can be written as 0 1 1 0 x1 x2. Okay. Now clearly t of v is same as a times v. Multiplication by any matrix is a linear transformation. Hence, this is linear. Therefore, this T1 is linear. Now, what will be the second case? Here, again, you can write T x1 x2. This is same as x1 comma 0. This is actually same as multiplication by this matrix. Okay. So T of V is same as, if you take denote it by B times V. Hence multiplication by, again it is multiplication by some matrix. Therefore projection is also a linear transformation. Now there is another question 3. It says T of x1 x2 is same as 1 plus x1 comma x2. What about this? This is actually not a linear transformation. Why? Because T of 0 vector goes to 1 comma 0, which is a non-zero vector. But under a linear transformation, 0 is invariant. Under a linear transformation, LT, denoted by LT. Therefore, T is not a linear transformation. Another question, T of x1 x2 is same as x1 square comma x2. Again, there is a nonlinear term. This is a nonlinear term, so it is. We can guess that this will be a non-linear transformation. So how can we say that? Here t of 0 goes to 0, 0. So we cannot. This property is also satisfied. Let us consider t of 1 comma 1. So not 1 1. T of 2 comma 2. By definition this is 4 comma 2. But what about t of 1 comma 1? This is same as 1 square comma 1, which is 1. Though 2 comma 2, this is actually 2 times 1 comma 1, but t of 2 comma 2, which is 4 comma 2, it is not actually same as 2 times t1 1. So t does not t does not respect the scalar multiplication. Hence t is non-linear. Similarly, there are another question. T x1 x2, it is same as sin x1 comma x2. Again, you can check that because we know that sine of x plus y, it is not actually sin x plus sin y. There is some other factors, that is sin x cos y plus cos x sin y. Hence, it is again a nonlinear, because if you check t of pi by 2 comma 0, this is actually sin pi by 2, which is 1 0, and t of pi comma 0, sin pi means 0, so 0 0. So this is not actually same as 2 times t pi by 2 comma 0. This is not same. Again, t is not respecting the scalar multiplication, hence t is non-linear, not a linear transformation. Okay. Next day we will discuss about linear transformation and a special case which is called linear functional. Is there any question? Is there any question?
No, sir.
Okay, great. If you have not any question, then you may leave.
Thank you, sir. Good session.
Okay, thank you. Thank you very much. Welcome.